KSP problems and type 1 problem where you're given the solubility and asked to find the KSP. So let's take a look here. We have the solubility of barium chromate is 1.4 times 10 to the negative fifth. So that's not very soluble. So even things that are, if you looked at your common ion chart, or not common ion chart, but solubility table chart, you'd find out that barium chromate is not soluble, but everything is soluble to some extent, but it has a very, very low solubility. All right, so how low is it? And we can do some comparisons of things with this. So the first thing I'm going to do is, for solving this problem, is just write the dissociation equation for barium chromate. When I dissolve that in water, even though very little dissolves, some will dissolve, and it breaks up into Ba+2 and CrO4 -2. That's supposed to be aqueous and aqueous, and this would be a solid. Pretty hard to see that, but that's typical of these KSP problems. All right, so with that, it is going, the KSP expression is going to be Ba+2 because that's aqueous, CrO4 -2, and we don't include the solid, so that would essentially be over 1. You could substitute a 1 in for that if you chose to do that. Not a 0, but a 1. So this is the KSP expression. Okay, notice it's a product. You're multiplying the two things together. That's why it's KSP, solubility product. So that's where that's coming from. So it says barium chromate has a concentration or a solubility of 1.4 times 10 to the negative fifth. So when that dissolves to the small extent that it does, what amount of, what's going to be the concentration of barium? What's going to be the concentration of chromate? Well, everything's in a 1:1:1 ratio. So if the solubility is 1.4 times 10 to the negative fifth of this, essentially 1.4 times 10 to the negative fifth, barium will dissolve per liter, and same thing with chromate per liter. So my concentrations are just a repeat of the barium chromate because everything's 1:1:1 ratio. So both barium and the chromate are 1.4 times 10 to the negative fifth concentrations. And I guess that would be in molarity. So what am I going to do? I'm just going to substitute these numbers in for the concentration of barium +2 and CrO4 -2. So I do that, 1.4 times 10 to the negative fifth times 1.4 times 10 to the negative fifth, I get 2.0 times 10 to the negative 10. And you're right, if you would have just squared that solubility in this case, you would have gotten the same answer. So that would be the KSP value. All right, let's do another example of this. Okay, but this time it's not going to have a 1:1 ratio, so it makes it a little bit trickier right here. All right, so the solubility of silver sulfide is 3.0 times 10 to the negative fifth. Find the KSP of silver sulfide. So I'm going to write my expression. So silver is +1, sulfide's -2, so it's actually Ag2S. So when this breaks up, it breaks into 2Ag plus S -2. Then I write the appropriate KSP expression. Okay, Ag plus gets squared, and then you get the S -2, and the solid isn't included. There's a 1 there, so we just exclude the 1 in the denominator. Now, when we think about concentrations, this is kind of like the double-decker ice cream cone that we have with the solubility of silver sulfides 3 times 10 to the negative 7th. I'm going to get twice as many ions as silver is sulfide. So the sulfide is going to also be 3.0 times 10 to the negative 7th when it breaks up, but my silver is going to be double that, or 6.0 times 10 to the negative, 17th, and not negative 7th right there. So notice the silver concentration is twice as much as the sulfide concentration because of that 2:1 ratio. So that's where I get these amounts. Now notice when I plug it back into the KSP expression, the one that I doubled because I have twice as much also gets squared. So you have to double it because you have twice the concentration. And then you have to square it because that's how KSP expressions work. And that's what we find true for the law of equilibrium constants, ends up matching out that way. So I square this, I keep this the same, and ultimately 10 to the negative 17th squared is like 10 to the negative 34th. and it looks like around 10 to the negative 51st with this here, but we got multiplying a couple sixes and a 3. It's close to that. It's 1.1 times 10 to the negative 49th is what I see. So this would be the KSP value. So why record KSP values and not solubilities? There is an appendix of KSP values, and you can look at it, and the smaller the number, the less soluble you generally think it is. So you're looking at this saying, hey, this is 1 times 10 to the negative 49th. This is 2 times 10 to the negative 10th. This is many orders of magnitude more soluble. Plus, it's going to be a way that we can solve, knowing a KSP value, it's going to be a way to solve for unknown like values of concentrations of things. Kind of like when you know a K value and you know one concentration, you can solve for another concentration. So that's a little bit more of the why. So this is a type 1 problem. Given the solubility, find the KSP. In the simplest form, it's just squaring it. But when you don't have a 1-to-1 ratio, then there has to be more algebra involved with that. Thank you. We'll do type 2 on our next thing.